Okay. Here you go. You guys can see that? This is very annoying. Okay. Perfect. So this is a gas cloud, right? This is full of all kinds of material in gas form, very hot gas. Likely the remnants of a supernova explosion, basically a star that exploded, right? Left all of its material out into space. And over time, that gas, due to gravity, clumped together, closer together, and becomes a disk, an accretion disk, they call it, right? And because of the way physics works and gravity works, something called angular momentum kicks in, and it makes basically that disk starts to rotate. And when the disk starts to rotate, you have heat build up in the center, much like swirling a cup of tea, right? What happens when you swirl it up? Well, stuff starts to build in the center, right? If you have marshmallows in there, they start building in the center. Same thing here. You have a lot of material build up in the center, becomes hot, and then over time, the star begins to, because it's a big ball of gas and plasma, it begins to ignite. And what this means is the material in it, deep inside the core, is so pressurized the particles are moving so fast so that when they bump into each other sometimes, there's so much energy in the process that it actually produces light outwards, right? So it produces a pressure outwards. And this is what light is. This is what keeps a star afloat. This outwards pressure in the form of energy, like light and radiation and other material. Then you have gravity keeping it inward. So the star's basically being equalized, right? Pressure inwards and pressure outwards, keeping the star afloat. And then from there, you have a shock wave. Typically, in the larger size stars, you have shock waves that push material outwards. And from there, you have a disk form where colder things on the outside become colder, right? The material that's left over, the remnants material, is flung outwards into space, becomes colder, becomes rocky, icy, and these eventually become planets, smaller planets, right? The smaller rocks in space, they clump together easily. In space, rocks and especially metals clump together very easily. They stick together almost like magnets. And so eventually you have larger planets. The larger ones suck in, like through their gravity, they suck in the smaller ones. They become larger and larger. They clump together, and then they form planets. So let me see if I can get a... This is how space and time expands. All parts of it are expanding, right? So we say we're here. This is our galaxy, right? The entire space and time, every single square inch of space and time is expanding outwards, right? This is how the Big Bang actually works. Now, if you notice from here to here, if you notice here is going faster, the expansion is happening faster further away. Here, the expansion is happening less fast, right? This is why the further away you are from us, the faster you are moving through space. The faster you're stretching away from us. The things that are closer to us aren't stretching as far. So there's something like it's like a rubber band that stretches apart our space and time, right? And it's happening in all areas of space. It has a center? No, because we can put this center here, right? The center is everywhere. Every square inch of the universe is the center of it, right? There's no one center. You can think of any coordinate as the center. Nothing's moving out from here necessarily. It's just there's nothing special about our place in the universe. It's that from any coordinate, you're going to see the same thing happening, right? Expansion going out from there, from every single coordinate of space. Dr. Kaku said there must be God. Well, God means different things to different people, right? God can be anything. God could be just the laws of nature. You can call that God. The point is, there's no evidence of a man that made us because of gravity. That's all. Why is the sky blue? Let's see if I have a photo of. So the sky is blue because oxygen is a nitrogen, actually, and oxygen. Well, more of oxygen. Most of the atmosphere is nitrogen, but a lot of it's oxygen. Oxygen molecules actually refract blue light. They absorb all the other light frequencies, but except for the blue, right? So blue is going to be scattered off of them, and that's what we see. Blue is scattered more than the other colors because it travels shorter and smaller and travels in shorter and smaller waves. Blue light is very short waved. Red is very long waved. So that's why red is typically what you're going to see during redder waves. You're going to see it during the nighttime because there are longer waves that reach your eye from they're long waves that reach your eye from a longer distance, right? In the sunset, when the Earth rotates, the sun is in a different angle from your eye, right? It's no longer in front of you. Now it's to the side. And now all that sunlight has to traverse all that sky. Whereas before, it was just going from the top to your eye, right? So when you look up in the sky is only 5 miles, maybe 7 miles max high. That's nothing, right? The sky is only 6 miles. That's it. But during the sunset, all that sunlight has to traverse all those hundreds of miles of air, right? So in that process, a lot of that blue light's going to be scattered, and you're going to see the longer wave. You're going to see the longer red light waves, and that's why sunsets tend to be redder. Because remember, when sunlight gets emitted in visible form, there's multiple colors within the visible light, right? There's multiple colors that your eyes can see. Because each color is a different frequency. So here, let me show you. Here's something that always fascinated me. So here are all of the. Let me actually mirror this because this is annoying. Okay. Here are all of the. Come on. Perfect. Okay. So here are all of the wavelengths of light. Gamma rays are the most intense because they are the shortest wavelengths. They're very short. Okay. In other words, sometimes the wavelengths are 10 to the negative 16 meters. Okay. So that's smaller than an atom, right? Well, atoms are, I don't know, but the size of an atom, right? Well, when we go up in the wavelength increase in wavelength, you can see here we have X-rays, UV rays, and this is what the sun produces here. The sun is basically generating infrared, UV, and X-rays, some X-rays, but mostly these. And between UV and infrared is the visible spectrum, right? And this is what we see. And this visible spectrum, these wavelengths are about 10 to the negative 6 meters, which is, like a nanometer or something. You can see here, its visible spectrum is divided into multiple colors, each with their own different frequencies. So the redder light is longer, the bluer light is shorter, like I said before. Right? Infrared is also typically heat. That's what we perceive as heat. And the microwave form is these are radio waves. These are longer waves. Some of these can be meters long. So some of the radio waves that are sent from your phone are this big, right? The wavelengths are this big. Sorry, this big. And of course, the more the smaller the wavelength, the more intense it is, the more frequent the amplitude, which means it's going to be higher energy, right? So all that means is light has higher energy depending on how fast, how quickly the amplitude, how short the amplitude is. Oh yeah, hopefully that answered your question. But yeah, we can barely see half of the light. Is it true that there are colors that exist somewhere that we've never seen? Well, yeah, there are many colors that, well, we only see colors because of our eye. Our eyes only filter in certain types of light visible in the visible spectrum, right? But our brain is actually what produces what you see around you. Your brain is actually what produces colors. Your eye just lets in the specific frequencies in. Now, in terms of other animals on the planet, some animals can see UV rays, right? Some animals can actually filter in UV light, which means that they would likely see different colors than we can. We couldn't really fathom their colors that they would see because our brains just can't comprehend all their colors. But a lot of bees can see it. A lot of snakes can see infrared. A lot of animals can see different colors and hence different frequencies of light. Your phone can see radio waves. Your phone, that's how information is sent through light, right? Information is sent through radio waves. Your phone receives, yeah, here. So these are lipid molecules, right? This is how the first cell formed, we think. These are lipid molecules. And the reason why they're in this structure here, right? These red ends and these other red ends, is because this side is, you can see there's two layers here. And the reason why there are two distinct layers is because this side is polarized towards liking water. This side's polarized towards not liking water, right? So that's why they form this sheet. It's called a lipid bilayer. So it forms a sheet. And then in water, you can see here how the sheet can connect with each other, form longer sheets, right? Longer film. And then look, because of the polarity of the two molecules, the two layers, it connects together into one sphere, right? One sphere. And look, now it's encapsulated. Now you have a outside structure and then an inner structure. That's it. That's how the first cell. This is one of the basics of the first protocell. And this is something we do in labs all the time. It's nothing magic. It's just basic chemistry. Basic chemistry. The ozone 3 that forms in the atmosphere. But here's a visualization of CO2 in the atmosphere. This is really interesting how this works. So you can see if we were to color CO2, you can see it being emitted in the northern hemisphere, right? Americas, Europe, right? This is the societies that pretty much produce the most CO2. So you can see they go into the atmosphere. Is it going to rotate? But you can see how what you do in one hemisphere affects the whole thing, right? So you have like this, they follow the wind patterns of the earth, starting to traverse into the southern side, starting to break into the southern side. And what this CO2 does is it acts like a blanket, right? So when we emit CO2 emissions, it acts like a blanket. It lets in sunlight and UV and infrared light, heat from the sun, but it traps it like a blanket. It lets it in, but it stops it from going out. So this is what we're doing to the planet, right? We're covering the planet in a blanket of CO2, and this is what's causing it to warm up. So CO2 is more important than the ozone. Well, the ozone is very important too, but it rebuilds itself over time, and it has. But CO2 is not as easily fixable, right? once it's in the atmosphere, it can take decades to get out of it. It can take decades to go into into the rocks, into the soil, into the water. A lot of it stays in the atmosphere for a long time. Could we survive if the sun went supernova? No, we would die. We would all be vaporized. The sun will never go supernova, though. The sun, when it dies, when the sun dies, it will become the size of a red giant. It will get larger and larger. So if you guys can see this here. So here we are now, right? The sun is doing good. In 4 or 5 billion years from now, the sun will become larger, the size of a red giant. It will be about roughly 2 or 3, maybe 2.5 times the size of it is now. It will engulf the earth almost. We're at the edge of it. So we would be at the edge of it and be just engulfed by it. First we'll be vaporized. First we would be vaporized by the intense radiation from it, but we'd also be engulfed by it. Mars might survive, but be basically a big molten rock. Then after that, it will shrink and then become a planetary nebula where it becomes a white dwarf and slowly strips away all of its plasma layers and become a nebula. The sun will not die very violently. It'll be actually very quiet, a very quiet death. This is what the sun would look like actually if it dies. It'll look very similar to this. Very beautiful thing where you have a white dwarf in the center that's stripping away its layers, and this is what's happening. These bubbles are basically the layers of plasma that are being stripped away from the sun over time. Is the space between two atoms also increasing? No. So on a local level, when we say we don't mean me and you. What we mean is the space in between the galaxies. The reason why galaxies aren't expanding themselves is because gravity is keeping them together, right? The gravity of a galaxy is holding it together enough so that it overcomes the force of the expansion. When it comes to atoms, the same thing applies, right? There's atomic forces at work that are keeping the atoms together. They themselves are not expanding. That's why. But again, it's space and time in between everything that's expanding, because there's nothing there to hold it together, so it succumbs to the expansion force. Can light travel at places where the universe expands faster than light? No. If the universe there are some parts of the universe that are expanding faster than the speed of light. That's the part we can't see. That's the event horizon of the universe. So the universe, like I said before, the graphic I showed you before, where the universe, the stuff that is closer to us is expanding slower than stuff further away from us. The stuff very, very far away is... Here's a better visual of it. So you can see everything is just expanding away from each other. The stuff closer is expanding slower than the stuff on the outside, right? So if you go far enough out into the universe, the space in between is expanding faster than light, which means that if light were to travel from there to us, it can never reach us. Because space and time would be traveling faster than light can even catch up to. But yeah, it's crazy how that works. Crazy. Did dinosaurs speak English? No. Can you explain G-force? What do you mean? Gravity? Gravity is just a warping of space. We don't really know what gravity is. we know gravity exists, but we don't know what gravity is. Gravity is still a mystery. Why did that fall? We still don't really know. I mean, yeah, we can theorize that the Earth is pushing down on this bottle, but that's not quite true. It's not actually quite true that the Earth is pushing down the bottle. There's something deeper at work there, and that's that the Earth, as it moves through space, is conjoining in coordinates with the bottle. So this is extremely difficult to imagine, but this is what relativity shows us, that space and time can warp itself, and things moving through space all are moving at the same time. Everything in the universe is moving at the speed of light. Everything in the universe is moving through the universe at the speed of light through space-time. It's just that all of our motion is in space, almost all of our motion's in time, almost none of it is in space. That's why we seem to be moving slowly compared to the speed of light, which has all of its motion in space and almost none in time. That's why light itself experiences no time. So the reason why this bottle is falling is because its trajectories between the Earth and the bottle are meeting in certain ways. Very difficult to grasp. Very difficult to grasp at a four-dimensional perspective. Very difficult. Can you explain quantum mechanics? Well, it's hard to grasp, but on the quantum level, things work differently than the macro level, right? When you're looking at it in an individual particle, for example, it doesn't have a definite location. Like on the Earth, I have a definite location. I'm here, right? I have my specific coordinates. I'm here no matter what. But on the quantum level, if you take a look at one particle, say an electron, that electron does not exist in any one spot. We don't know. We cannot predict where it is. In fact, there's something called the uncertainty principle, which demonstrates we will never be able to determine the exact location of a particle. All we can do is measure how likely it is to be in a specific area. And this is basically the uncertainty principle. We can never be certain about where it is. That's all that means. We don't know why. That's just how the universe operates. Particles work really weird. There's entanglement where if a particle is... There's these quantum connections to particles that we just don't understand yet. There's all kinds of superpositions where a particle can be in different states at one time. It can be in different locations at one time. It can split. It can teleport. It's really weird things happen. Really weird things happen at the quantum level that just don't happen in the macro level. Do you think a warp drive is realistic? Yeah, warp drives are realistic because all you're doing with a warp drive is pushing the space in front of you. See, if you're traveling through space-time, you can't go faster than the speed of light. It's impossible. But space and time itself can travel faster than light. It's easy. So if you can manipulate space-time, if you can warp it in a way that allows you to ride the wave of space, well, now you can travel as fast as you like to. You can bypass the speed of light and go as fast as you want. So warp drives are theoretically possible. You just need lots of energy to keep it going. And we don't know. You'd have to You'd have to have enough energy to warp space and time enough to do that. Um, yeah, you need negative energy to push space in front of you. How would we build a wormhole? Energy. Everything is energy. Like, if you have enough energy, you can build a black hole, right? If you have enough mass, you can build a black hole. Same thing with with a wormhole. If you have enough energy, you can build a wormhole. But you also, if you want to travel through it, you have to keep it open. See, a black hole is constantly being closed because gravity keeps pushing it together. But if you want to keep it open, you need lots of energy to keep it open, right? So you need positive energy to cut through space time, but then you need negative energy to keep it open. So you got to push it. So you have to push it outwards so you can travel through it. And that's how you do it. You need negative mass, negative energy. And when you get this negative energy is from space and time itself. All space contains energy. Even in the most empty space, there's energy fluctuating, quantum fields fluctuating. Even the empty, in fact, there's more energy in space than there is in your mass. About. If everything's made of atoms, how can it be that anything is solid? The states of matter are just the vibrations of the atoms in a given material. In a gas, the atoms are moving very quickly, right? They get very excited. They're high energy particles. That's why it's a gas form. In liquid, the particles are less energetic, the more condensed form, right? So the atoms are moving much more slowly. In a solid, the atoms are moving almost nothing, very, very compact together, and the atoms are not moving much at all. That's all what it means. That's all it means to have different states of matter. If if they're massed with enough force that if it hit the moon, would it shift orbit? Yeah, of course. Of course. In fact, the orbit of the moon is already unstable. The moon is actually moving away from us, like I think 2 inches every year. They're moving. 3 billion years ago, the moon was much more closer to the Earth. The moon was very close. In fact, the tides were not just in the oceans, but even lakes and ponds. Even in small lakes, there were tides. Even small ponds, there were high and low tides. That's how close the moon was. And it's moving away from us every year, about 2 inches. And eventually, in the next billion years from now, the moon will be far away that it actually won't cause tides anymore as much. Can a needle moving at the speed of light destroy a plant? So nothing with mass can move at the speed of light. But if you were going to go close, like just about at the speed of light, just before it, yes, a needle would have enough energy like of a bomb. A needle moving at the speed of light would have enough energy to explode your house. It would be like a car exploding. So yes, it would definitely destroy a plant and perhaps even your house. And and if you had something increasingly heavier than that, like a car, it would have enough energy to destroy a country. How do black holes bend space? Everything bends space. Even you do. You're bending space right now. Just a much smaller degree than a black hole. But everything with mass bends space. Everything that has mass bends space. It warps it. Even time. Time also warps, just like space does. Time warps. But yeah, if you have enough, it's like a fabric, right? If you have enough, if you have a bowling ball in a fabric, stretched out fabric, what happens? It's a big indent, right? And things that are smaller have less of an effect. Does time feel as if it's passing the same if someone were to travel in space? Yeah, no, time always feel like to your perception of time is always the same in terms of what you're saying. Um it's just that from if I were to go into if you were to stay on Earth and I were to go into a spaceship to another place in space, relative to your watch, my watch will be different, right? Relatively speaking, my watch on the spaceship will be vastly different than your watch on the Earth. That's where relativity comes in. That's the spooky part about the universe, right? It doesn't. It's not intuitive to us. But on the spaceship, you would feel normal. You would feel as if this is normal, right? You would feel the same as if here you were on the Earth. But your time on the clock will be different, noticeably different, verifiably different than somebody on the Earth. And this is something that we know happens. It's time dilation. We can measure it. Nobody has the answers. Nobody does. Why did humans stop growing hair on their bodies like other apes? We never stopped growing hair. We still have as much hair as the other apes. It's just that it's thinner. And the reason why is because we developed clothing. We started to live in warmer climates. We walked further. We sweat more. We needed to. We sweat the most out of all the other apes. We sweat the most by far. So sweating has a lot to do with it. Keeping ourselves cool had to do with it. Clothing as well. Imagine thinking you're smarter than the one who designed the brain. Well, if you're gonna let's use this logic reversed. We can say, well, if our brains require intelligence, who designed your intelligence? Who designed that intelligence? If you're going to say that our intelligence requires intelligence, then who designed that intelligence? And we could go on and on forever. We can go on and on forever. Don't you see? You're kicking the can down the road. That's all you're doing. You don't need a designer. You can stop at a universe that makes things happen naturally. That's all you need for intelligence. You don't need God. Your logic is bad. It doesn't work. It doesn't answer anything. It doesn't solve anything. That's why God is a useless thing. It solves nothing. All the mysteries in the universe, saying God did it does not solve one bit of them. Not a single mystery has been uncovered by saying God did it. Remember that. Can you explain how we went from hunter-gatherers to building pyramids in 10,000 years? What made us so special as a species was civilization. As soon as we invented agriculture, as soon as we invented growing food, right? Habitats, shelters, roads, the wheel, these things dramatically changed our species. As soon as we invented languages and paper, right? these things made us human. It's not that there's nothing special about it. If you take a person from a couple hundred years ago versus a chimpanzee, there's not much different. There's not much difference. They don't know. It's not that we humans are special, magical aliens that know everything. It's not. It's not that we're that much more intelligent individually. It's that collectively speaking, that's when we shine. That's when humans shine. When we work in collective groups, we have the fact that we can share language with each other, the fair way that we can understand and communicate with each other in ways that no other animal can. That is what makes us human, and that's what allows us to build pyramids and go to the moon. Working together, and cooperating with each other. That is what makes us human. This is what whales used to be like. That's incredible. That's amazing to understand. About 50 million years ago, right? So you go from here to here, to here, to here, to here. Dolphins and whales, dolphin-like animals, and then whales. That's why whales are mammals, right? Why it doesn't make sense that whales are mammals if you think that God designed us, but it makes more sense that they evolved to be that way because they moved into the land, they moved into the waters over time. This is amazing. Here's a bigger picture for you guys to see. Do you see? See how it developed webbed feet? See that? Right? And then if you take a look at the nose, whales actually don't breathe underwater. They're not fish. They don't breathe underwater. They can't absorb oxygen from the water. They have to breathe air from the outside. That's why they have these noses. That's what their snouts are for, right? They have to breathe air, they have to push air out and breathe it in. And that nose can be traced back to Pakicetus. But what happened was the nose went further and further up their skull. And that's quite literally what a whale is. And the arms became fins, just like the fins on the earth on the land became arms for humans. And if you go back to here, the homologous structure, we can see this, right? We can see that the human hand has the same bones as a whale's hand. The same bones. It's the same bones. Fingers, right? The hand bones here, the carpals, the thing that makes it rotate. You have the ulna, the carpals, all the same bones in a whale fin. The reason why is because we share common ancestry with them about 60 million years ago. But since then they diverged. Same with cats. Cats and bats. The bone structure of a bat is the same as the structure of a human. It's the same structure. They're homologous structures. They even have 5 fingers. Right? The reason why is because they share common descent. This is the evidence for evolution. This is direct evidence of evolution right in front of you. Analogous structures as well. These are slight differences. But they're different structure, but with similar function, right? So if we can compare bats to birds and butterflies, right? The bone structure of the bat is closer to the bone structure of a human arm than it is to a bird, right? So we can see that the bird diverge even further away from the bats than humans. So birds are further away from us than the bats are, and this is directly what the DNA evidence confirms. So when we look at analogous structures, we know how far away they are from us in descent. When we look at homologous structures, that tells us how close they are in descent to us. So these are ways of confirming evolution, let alone DNA, right? Let alone the fact that we can see our DNA. We can see this all in the DNA sequencing. How were monkeys created? monkeys weren't created; they evolved, just like everything else. But when we say we come from monkeys, what we mean is we share a common ancestry. But monkeys themselves. Here's the image that I'd love to show you guys. Okay, so here's a great image. I love this image. This is a new image I've never seen before. So here's the modern day human, right? You go back further, they look more ape-like, right? They were not bipedal. They walked on they walked on all fours. They resemble more chimps, right? And then further back here, you have more monkey-like animals. And this is about 50 million years ago. Now, where do monkeys come from? Well, they come from prior mammals, squirrel-like mammals, right? This one looks like a squirrel or a rat. And this is one of the mammals that survived the dinosaur impact, right? 65 million years ago, the dinosaurs died. This gave way for mammals to survive and thrive in trees. And thank you. And this allowed the mammals to become different and proliferate and become different. If the dinosaurs never died, we would never have been here. Wait, I want to see the poll. It looks like 90% of you guys learned something today. Okay. Yeah, so here we are. So monkeys, where do monkeys come from? Well, they're prior mammals. They were eggless, marsupial type like animals. They had nipples, they had placenta. These were the first mammals. Where do they come from? Well, mammals came from reptiles. You can see about 260 million years ago, you have one of the first mammals emerge from the reptiles. We diverged from the reptiles. We developed milk glands, sweat glands, hairy skin, specialized teeth, constant body temperature, right? We started sleeping during nights, eating during the day. And that's how mammals emerged. And then now when it comes to reptiles were products of the amphibians, right? The amphibians, which come from lizards, things like that, amphibians that could live on land and water, right? And before that, they obviously came from fish. And every land animal on the planet stems from what we think is Tiktaalik, which was about 400 million years ago, the first fish-like species that walked on land and had arms that could barely walk on land, mostly live in water, but could also live on land. And we think that they gave birth on land and was able to survive on the surface. And before that, fish, right? Before 400 million years ago, all life, except for cyanobacteria, was in the oceans. That's incredible to think about. Living land things are new. We're brand new to the earth, right? Even trees are new to the earth. Trees are only 400 million years old. Before that, there were no trees. They didn't exist. When the dinosaurs existed, there was no such thing as grass or flowers. It didn't exist. There was no grass, there was no flowers. Those things evolved over time, just like everything else. And that's how we got here. And if you go back to the first living thing, well, Mike, what's the first living thing? Here, it's right here, a protocell, right? It's a RNA molecule. That's all. It's just a molecule. That's what life is. Life is a chemical thing. It's not magic. It's not God. It's not Jesus. It's just chemistry. Simple chemistry becoming more complex over time. In fact, there was a lot of biodiversity before humans, before living things on land. Before, in the oceans, life was very biodiverse. Life was extremely diverse in the oceans. It survived there for billions of years. lots of living things exist in the oceans, probably things we have no idea about. What is my favorite species? I don't know. I don't have a favorite species. I like all living things. See, the great thing about science is that the more you learn about things, the more you appreciate everything. I appreciate all living things. How do they teach people about science yet they're so misinformed? Yeah, it's because school does not teach you. Modern day school doesn't teach you. It only tells you things. And the problem is that school does not teach you the methodology of how you know these things, right? School never tells us how we know these things. When you're force-fed facts, when somebody tells you, like what happened on this live, right? When I told facts and people in the comments are like, no, that's impossible. That's impossible. It's because if you don't know the methodology of science, you're going to be lost, even if somebody tells you the facts. So it's like you need to know how to know things. That's more important than just knowing something, right? What's more important than knowing something is how you got there. And school does not teach that. It does, but not to a sufficient enough degree. School is simply testing you on how to know. School assesses you on your ability to remember things or memorize things. That's cute, but it doesn't actually make you think critically. School rarely talks about how to think critically, and that's the point. That's why you get people like we have today, where they don't know anything, because they don't know how to think, right? Science is not just a collection of facts, it's a way of thinking. So if you know how to think, well, then you can know anything. Once you know how science works, anything somebody tells you, you can now assess. Now you can properly assess it. But when you're just simply told facts, you don't know how to absorb it correctly. And that's why you become skeptical. Which is good. The skepticism is great, but you're using it in the wrong way. You're using it in the wrong way. It's being misplaced. Why haven't we been back to the moon yet? Because it's expensive. People don't realize how expensive it is to go to space. The reason why we went to the moon in the first place was because of the Cold War, right? We went up to prove to the Russians that we can beat them in space. And we did. Once we beat them, we went back to Earth, right? Because there's no motive anymore. There's no motive to do it. It cost us hundreds of billions of dollars. Did you know that it cost us hundreds of billions of dollars to go to the moon? Hundreds of billions. Do you have that money? NASA doesn't have that money today. NASA today does not have that money to go to the moon. The Artemis mission took 10 years of planning. It took 10 years of budgeting and planning to come to fruition. And it's not going to get here. We're not going to actually be on the moon until 2026. So think about it. How much planning has to occur? How much money has to go into it? The motive. And by the way, it's dangerous going to space. It's dangerous. The Apollo missions were way more dangerous than they are today. So the missions to space today are more safer, which also require planning and missions, right? And money, right? Think of how much research has to go into making it safe. So if you think binarily, if you think that everything's black and white, of course you're going to be confused. Why aren't we back with the moon? Why didn't we go back? You have to realize that it's much more nuanced than you think it is. It's much more complex than we either go or we don't go. It's not how this works. when we went to the moon, we knew the Apollo astronauts. Did you know that the Apollo astronauts on the first mission, they literally thought that they didn't work. They thought that they would die. They went to the moon knowing that they would likely die and never come back. Think about that. Think about that. They thought that there was a greater than 50% chance that they would die. See, it was risky and expensive. Okay, that's why we didn't go back. But now, as space has become more safe, a little bit more cheaper, we are, and there's now a motive, because the reason why we're going to the moon now is because it'll give us more insight on how to go to Mars, right? The Mars is the big goal. Mars is the big daddy, right? The moon is the step there. There's nothing on the moon. There's nothing there. It's just dust and rocks, right? But Mars is a different story. Mars has potential habitat, space, and things like that. The point is that if you don't have motive, if you don't have money, if you don't have the balls, you're not going to go to space. What's the temperature on Mars? So it's cold. Near the poles in the winter, it's almost negative 200 degrees Celsius. Very cold. But in the summertime, at the equator, it's almost 60, 70 degrees Fahrenheit. That's like 20 degrees Celsius. Very hospitable. But the thing is, you can't live on the surface unless you are covered in a dome or covered in something that can protect you from the radiation from space. Because remember, Mars does not have it has a magnetic field, so you would be bombarded by radiation from space. Spreading false info. Okay, great. What's the false info? What false info? I would be glad to correct myself if you can demonstrate where I'm wrong. That space is real? You think space is fake? You think space is fake when you can see it with a telescope? What do you think you see when you look up at a telescope? You think that's just CGI? That's just the Truman Show? There's a guy up in the ceiling. Oh no, he's looking at the star. Let's fix it. Beep, beep, beep. All right, guys, bring the star back up. No, that's not happening. Oh no, he's looking at the telescope again. Let's change. Let's make this galaxy bigger. All right, guys. Cat far. No, that's not happening. How do you think the universe started? It didn't start. Why do people assume it started? Why? What do you mean by start? What do you mean by start? These questions don't mean anything. They don't mean anything scientifically. Wherever you say it started, there could be something before that. Wherever you put the starting point, it's irrelevant. It's arbitrary, right? We don't know what these terms mean in terms of the entire universe. We don't know much about the universe to even suggest that there's a start or not. We don't know what these terms mean. All we know is that the universe is expanding, and if it's expanding today, it must have been smaller in the past. That's all we know. We don't know more than that. So stop pretending as if we know more than that. Religious people love to exploit the ignorance of our current understanding. God resides Gaps in our knowledge. Just like Neil Tyson says, right? Neil Tyson says that God is an ever-receding pocket of scientific ignorance. Theists always look for the gaps in our knowledge to fill God in, right? Oh, we don't know how the universe started. God did it. Oh, we don't know what black holes are. Oh, God's in there, right? You're always looking for something to fill, literally and metaphorically. So the point is, stop believing in things that we don't know enough about and start asking more questions about what you're talking about. Where did all the energy come from that triggered the quantum fluctuations? It's in the quantum field itself. It was always there. Again, quantum fields vibrate, they fluctuate, and because of those fluctuations, they hold potential energy that then becomes kinetic energy, which means inflation. It means an inflationary universe. That's the point. Quantum fields contain energy, always. They always did. But they fluctuate and they can yield universes, yield something like our space-time. And there's probably other quantum fields. There could be an infinite number of them, each producing all kinds of universes. Do I believe in the CCC theory? No, I don't. There's no such thing as believing in a theory. It doesn't make any sense. A theory is simply an explanation. It's a model, right? Nobody believes in theories. A theory is a mechanism for reality. It's a mechanism. Especially in science. We don't believe in theories in science. What happens is a theory is what describes the fact, right? The fact is what we understand and know. But we don't go, oh, let me believe in this theory. Yeah, that sounds like a good theory. That's not what happens. That's not how science works. We don't go, well, I'll believe in that one today and then that one tomorrow. No. We are driven in science by the evidence, not by belief, but by evidence, right? Is the evidence sufficient enough to describe this phenomenon being the most likely scenario? Yes or no? If yes, we take that as the best model available. If not, throw it away. That's how science works. We don't sit there and but I have the Bible. The Bible. The Bible. The Bible. The Bible. The Bible. We don't, 2,000 years later, the Bible. We don't do that in science, okay? We actually change and improve and get better. I know that's a hard thing to fathom. All right. So we can think of the universe as a block. So this is one model. This is one model of the universe. Relax. This isn't what I believe. This is just a possibility. Okay? It's a possibility. So there's three possibilities in terms of how Einstein, or how, we can metaphysically understand time, right? There's presentism, which says there's only the present moment, right? The future doesn't exist. The present is gone, right? The past is gone. The present is the only thing that exists. Then there's possibilism, which says the past is still here, but the new futures are always becoming different. Then there's the block universe. This is called eternalism, which says the past and the future both exist. And the present is just our way of understanding the difference between these two, right? So those are the three different models. Einstein comes in with relativity and shows us evidence that supports the block model. In that, remember guys, this is a three-dimensional perspective of it. You can't, it's hard to fathom this being four dimensionals, but they made it simple for this. Imagine space being a dimension of the universe, and so is time a dimension of the universe. So imagine dimension of space and dimension of time in a block, right? So just as space is static and always there, so is time. All of time is static and always there, right? It's a block, right? A block of cheese is always there. It doesn't change, right? So think of a block of cheese. It's always there. All the ends are there. The future of it, the past of it, the same thing with here. And the now and here is just one coordinate within the block model. That's all. So again, all of time and space may exist. And statically, it all exists and nothing happens, right? Einstein's block universe in which nothing happens, objectively speaking. Anything that happens within the block is relative, right? So again, this is a very simplistic way of viewing it, but that's how it works, very simplistically.